In today's discussion on industrial instrumentation, we will talk about flow measurement. The contents of today's discourse are definition of flow, fluid types, Reynolds number, units of flow measurement, types of flow, Bernoulli equation, the basic requirements for a flow measurement, factors that affect flow meter performance, selection of flow meters, definition of quantities to be measured, that is volumetric flow rate and mass flow rate, calibration methods for flow meters for both gases and liquids, Coanda effect and Coriolis effect. Flow is the motion characteristics of constrained fluids that can be liquids as well as gases. It deals with two things, how much, that is total, and how fast, that is rate. Then the next term is viscosity. Dynamic or absolute viscosity is measured in terms of eta. It is a measure of the resistance to a fluid to deformation under shear stress, or an internal property of a fluid that offers resistance to flow. Fluids can generally be divided into two types, Newtonian fluids and non-Newtonian fluids. When held at a constant temperature, the viscosity of a Newtonian fluid will not change regardless of the size of the shear force. When held at a constant temperature, the viscosity of a non-Newtonian fluid will change with relation to the size of the shear force, or will change over time under a constant shear force. Given here is the figure that depicts the Newtonian flow and the non-Newtonian flow. The Reynolds number is the ratio of inertial forces to viscous forces of fluid within a pipe and is used to determine whether a flow will be laminar or turbulent. Numerically, Rd is equal to Vd rho by mu, where Rd is the Reynolds number, V is the average velocity, D the inner pipe diameter, rho representing density, and mu the absolute viscosity. We spoke about Reynolds number and how Reynolds number define the flow types. Based on Reynolds number, there can be three flow types: laminar, turbulent, and transitional. Laminar flow occurs at low Reynolds number, typically less than 2000, where viscous forces are dominant. Laminar flow is characterized by layers of flow traveling at different speeds with virtually no mixing between the layers. The velocity of the flow is highest at the center of the pipe and lowest at the walls of the pipe. The second type is turbulent flow. It occurs at high Reynolds number, typically at least more than 4000, where the inertial forces are dominant. Turbulent flow is characterized by irregular movement of the fluid in the pipe. There are no definite layers and the velocity of the fluid is nearly uniform throughout the cross-section of the pipe. Third is the transitional flow. Typically, it occurs at Reynolds number between 2000 and 4000. Flow in this region may be laminar, or it may be turbulent, or it may exhibit both the characteristics. The figure shows examples of how laminar flow and turbulent flow moves along the pipe. The units for measurement of flow can be of several types based on the specific process and the information requirement. Basically, it can be of three types: solids, liquids, and gases, and there is a fourth type, steam. For solid, it is expressed in weight rate like tons per hour or kilogram per minute. For liquid, it is measured in weight rate and in volume rate both, like tons per hour, kilogram per minute, liters per hour, liters per minute, meter cube per hour, etc. For gases, it is expressed in volume rate at NTP or STP, like STD, meter cube per hour, or N meter cube per hour. For steam, it is expressed in weight rate, just like the solids, like tons per hour or kilogram per minute. The steam density varies with changes in temperature and pressure. The measurement is converted into weight rate of water, which is used to produce steam at a point of measurement when we are measuring steam. Flow meters can be characterized in a plethora of ways. Here we see that flow meters are characterized based on whether the flow measurement is of steam or of gas or of liquid. For steam flow measurement, we use vortex, dP flow meters, multivariable flow meters, and turbine flow meters. If we are dealing with gas flow, We normally resolve to vortex, DP flow meter, multivariable flow meter, turbine flow meter, which is similar to that of steam, and in addition we have thermal mass flow meters. If you are dealing with liquid under flow, it can be of two types, conductive and non-conductive. For conductive, it can again be of two types, clean and slurry. And for non-conductive, again there are two types, clean and slurry. So for liquid flow meter, which is of conductive in nature and clean, we resolve to vortex, DP flow meter, Coriolis flow meter, ultrasonic, turbine, water meter, and electromagnetic flow meters. And if it is of slurry type, we take help of DP flow meter, Coriolis flow meter, ultrasonic flow meter, and electromagnetic flow meter. Coming to the non-conductive liquids, for clean ones, we take help of vortex, DP, Coriolis, ultrasonic, turbine, and water meters. And for slurry ones, we go to DP flow meter, Coriolis flow meter, and ultrasonic flow meters. A flow can be of both of two types, that is closed channel flow and open channel flow. The most common devices and techniques that are used in measurement of closed channel flow are orifice flow meter, venturi flow meter, nozzle flow meter, pitot tube flow meter, wedge flow meter, vortex flow meter, ultrasonic flow meter, turbine flow meter, and magnetic flow meter. We'll come across each of these particular flow meters and see how they operate and what are the principles behind this operation in our subsequent slides. When we speak about flow and flow measurement, Bernoulli's principle plays a vital role in it. Bernoulli's principle states that a rise or fall in pressure in a flowing fluid must always be accommodated by a decrease or increase in the speed, and conversely. That is, an increase or decrease in the speed of the fluid results in a decrease or increase in the pressure. Numerically, P equal to half rho V squared plus rho GH equal to constant, where P is the pressure in the system, rho is the density of the fluid under measurement, and V is the velocity of the fluid. H is the static height of the flow under consideration. Thus, if we divide the equation by rho, we get dds of V square by 2 plus P by rho plus GH equal to 0, which is a constant. Thus, we can say that V square by 2 plus P by rho plus GH equal to constant. Substituting gamma for rho g, we get V square by 2g plus P by gamma plus H equal to constant, which gives us rho V square by 2 plus P equal to constant. Thus, if we consider a constriction in the path of flow, and on either side we have components termed as suffix 1 and suffix 2, we get rho V1 square by 2 plus P1 equal to rho V2 square by 2 plus P2, and they should be equal to hold Bernoulli's equation true. In the process of flow measurement, there are few elementary requirements that need to be met. These requirements are the ability of the flow meter to be calibrated, the ability to integrate the flow fluctuations, easy integration with the piping system. It should offer high accuracy and high turn-down ratio. The cost involved should be less. It should be less sensitive to dust particles. The pressure loss in the system should be as low as possible. The system should not have moving parts, and the resistance to corrosion and erosion should be very high. In the process of flow measurement and its performance, there are few factors that influence and affect the flow measurement output. These factors are process media, which can be gas or liquid, the temperature of the environment, velocity of the fluid, viscosity of the fluid, pressure around the fluid, and the density of the fluid. Here we'll have a brief understanding of how flow meters are classified. Basically, all flow meters can be broadly classified as volumetric flow meters and mass flow meters. Furthermore, it can be categorized as differential pressure flow meter, positive displacement flow meter, velocity flow meter, mass flow meter, and open channel flow meter. When we speak about differential pressure flow meter, it can be orifice plate, venturi tube, flow nozzle, pitot tube, elbow tap, target flow meter, and variable area flow meter. In all these type of flow meters, Bernoulli's principle is a very important factor. That is, we create a pressure difference on either side of the flow profile, and based on the pressure difference profile, the flow measurement is done. Then we have positive displacement flow methods, which can be reciprocating piston, oval, gear, newtating, disc, rotary, vane. For the velocity flow measurement, we have turbine flow methods, vortex shedding flow meter, swirl flow meter, Quantities effect flow meter, momentum exchange flow meter, electromagnetic flow meter, ultrasonic flow meter, Doppler ultrasonic flow meter, and transit time flow meter. Mass flow meters come as two types, Coriolis and thermal. Then we have the open channel flow meter, where fluid passes in open channel networks like that in drains and canals and rivers. There are basically two important types to measure this kind of flow. They are wear and flume. While we carry out the selection of a flow meter, there are many factors that we should keep in mind. These factors are the measuring medium, that is, it is gas or vapor or slurries. We also take into account of the application of the flow meter, that is control based action, monitoring based action, or just a supply flow device. The operating conditions also play a vital role in selection of flow meters, like temperature, pressure loss, range, ability. All these factors, they come and play a considerable part. The installation condition, like bore or upstream or downstream, piping work or explosion proof, this also has good say in the selection of flow meters. If you talk about the instrument performance, accuracy, velocity, range, sensitivity, speed of response, all these factors are also to be taken into consideration. The factors which are to be kept in mind while choosing a flow meter for a particular type of flow are accuracy, safety, installation, and cost. These four factors play the most vital role in selection of flow meters. Broadly, there are two types of flow, volumetric flow and mass flow. The volumetric flow rate is given as V equal to A into V, and the unit is meter cube per hour, where V is the velocity flow rate, A is the area of cross section, and small v is the velocity of fluid. For mass flow rate, the expression is given as m equal to rho into capital V, which is equal to rho into A into small v, and the unit is kg per hour, where mass m represents mass flow rate, v is the volume flow rate, rho is the specific density of the fluid, A the cross-sectional area, and small v the velocity profile of the fluid. Just like any other instrument, the flow meters also require a very vivid and elaborate calibration before they are put into use. Based on liquid flow, the calibration can be of two types, in situ calibration and laboratory calibration. In situ calibration, there are again two types, insertion point velocity method and dilution gauging or tracer method. For the laboratory calibration method, it can be of four types, master meter, volumetric, gravimetric, and pipe prover. When we are dealing with gas flow, the calibration methods again come under two categories, in situ and laboratory. The in situ calibration methods are same, that is insertion point velocity method and dilution gauging or tracer method. In the laboratory method, there are three types, foam fill burette method, water displacement method, and gravimetric method. Now, what is this insertion point velocity method? It utilizes point velocity measuring devices where calibration device chosen is positioned in the flow stream adjacent to the flow meter, being calibrated and such that the mean flow velocity can be measured. The second type is the dilution gauging or tracer method. It finds application in both open channel and closed pipe flow meter calibration. A chemical or a radioactive tracer is injected at an accurate measured constant rate, and samples are taken from the flow stream at a point downstream of the injection point, where complete mixing of the injected sample has taken place with the water. There are two very important effects when you talk about flow and flow measurement. They are Coanda effect and Coriolis effect. Coanda effect is the phenomena in which a jet flow attaches itself to a nearby surface and remains attached even when the surface curves away from the initial jet direction. The Coanda effect is the tendency of a fluid jet to stay attached to a convex surface. In free surroundings, a jet of fluid entrains and mixes with the surrounding as it flows away from a nozzle. A moving stream of fluid in contact with a curved surface will tend to follow the curvature of the surface rather than continue traveling in a straight line, and that particular nature of phenomenon is known as Coanda effect. For example, when we pour tea or water from a beaker or a kettle, we see that the tea tends to cling to the inner surface of the kettle or the beaker. This is because of the Coanda effect. Here we see the pictorial representation of Coanda effect. The diagram shows that increasing the angle of attack increases how much the air is deflected downwards. If the angle of attack is too high, the airflow will no longer follow the curve of the wing. Coanda effect is losing the power. As shown in the bottom of the diagram, this creates a small vacuum just behind the wing. We can say that the wing is stalled as the air rushes in to fill the space called cavitation. It causes heavy vibration of the wing and greatly decreases the efficiency of the wing. This effect is used in lifting and braking of the aeroplanes. The velocity v of an inviscid two-dimensional flow of a free jet for Va velocity along the free streamline is given as v by Va equal to exponential 2h by pi r tan inverse sin h squared pi theta r by 4h minus cos h squared pi theta r by 4h tan h squared pi gamma r by 4h whole under square root, where h is the width, r is the radius of cylindrical surface between the first contact A and the separation at B, theta is the deflection angle, gamma is the angle along the wall, it is 0 for A and theta for B, and h by r is the relative curvature. The pressure change that is created in this particular vacuum denoted by PA can be calculated by employing Bernoulli's equation. The second important effect is the Coriolis effect. Coriolis effect is a deflection of moving objects when the motion is described relative to a rotating reference frame. In a reference frame with clockwise rotation, the deflection is to the left of the motion of the object. For counterclockwise rotation, the deflection is to the right. Numerically, it is given as Fc equal to minus 2m omega v. That is, Coriolis force is the product of 2 into object's relative mass into angular velocity into the rotating frame velocity. Here we see the pictorial representation of a Coriolis effect. For more detailed and more elaborate studies, the viewers can refer to the following references. Thank you.